So now we're going to decide, or we're going to discuss this bilinear transformation, right? So we already have taken care of step number two. So now if we have the analog filter in the S domain, how can we convert it into a digital filter in the Z domain, right? So what transformation to use? Okay, so let's do that. Let me just go here. Sorry? Step three, yes. Okay. Now, this is essentially a transformation or a conversion or a mapping from Z domain to S domain, right? S to Z or Z to S, right? Now, why do we need this mapping? We already had learned the mapping, Z is equal to e to the power st, right? We learned that. Now, this mapping is nonlinear. So if you want to get, like, for example, what is S, for example, from here, so you will need to take the log of both sides. So we'll get like log of Z equals S times T. So S is going to be essentially log of Z over T, right? So, and then, when you apply this transformation, it's going to be not possible to implement the filter because you need the coefficients of Z, right, to implement the filter. So this transformation that we will study is essentially an approximate version of this one. Okay, so let's do that. And for that, let's have like sort of an integrator setup in the case of the continuous time domain. So let's say we have, let's say, a signal on this time axis, right? So continuous time signal that looks something like this, right? So this is x of t, right? Now suppose we have an analog filter. What it is doing, it's just integrating the input. So we have y of t, which is just doing the integral from 0 until t. Yeah, so far so good. So you have an integrator that is integrating the input. What we will do, we will try to approximate this system for the case of a digital system, right? And then relate the transfer functions together. By the way, if you want to find the transfer function for an integrator, what do? You just take the S transform of both sides, right? So what is the Laplace transform for an integral operation? It's fine, you don't remember. Yeah, you're right, 1 over S. Yeah. So the take the Laplace transform of both sides, you will get x of s equals y of s equals x of s over s, right? And from here, you can find the transfer function of this integrator process. It's going to be g of s equals y of s over x of s, that is equal to 1 over s. So this is a transfer function representing continuous time integrator. Okay. That is what it's doing, is like, it's just, suppose this location is t, right? So it's just integrating the input until this point. Clear? Now what we do, let's say we sample the signal, right? So let's say we sample the signal. The sampling interval of t seconds, right? And let's say if this is, for example, sample number 0, this will be sample number 1 times t in terms of terms of seconds. Sample number 2 times this sampling interval t seconds. Sample number 3 times the sampling interval t seconds, and so on and so forth, until, let's say, this one is sample number n. So this is sample time n times t seconds, and this guy is going to be n minus 1 times t seconds. Right? Okay. So let's say our digital integrator has done its job until sample number n minus 1. That is time n minus 1 times t. Okay. And now what I want the output of the integration process for sample number n. That is, I need to find out, let's say, y of n, right? And I know y of n minus 1. That means I know the integration approximation until n minus 1th sample. So I just want to find the approximation of the output of the integrator for sample number n. So how we can find it out? One possibility is like I take the output until n minus 1 sample, right? And then I add to it the average signal value during these t seconds times t. That means if this is the input signal value at x of n minus 1, so this is, let's say, x of n minus 1, right? And this is, let's say, x of n. I find their average, right, for this time duration of t seconds, and then I multiply with this t. It's like, approximating it with like sort of a rectangle, right? So that will give me the area under the curve, because what is integration doing? It's just giving you the area under the curve, right? Okay, so that means I can write the same thing as y of n equals y of n minus 1 plus the average of the signal value, which is going to be x of n plus x of n minus 1 over 2 times t. Because the signal value at sample number n is x of n. The input signal value at sample number n minus 1 is x of n minus 1, right? So if you want to approximate the area for that particular region, it's going to be x of n plus x of n minus 1 over 2, which is the average height of the input signal during this time, times the time, which is t seconds. Sorry? Okay, again. What we're doing here is we are trying to approximate an integration process. What does the integration process do? It just computes the area under the curve, right? So let's suppose I'm giving as input x of t to a system, and the system, what is doing is just computing the integral of the signal until time t. Yeah? Sorry? I, I want to take the approximation of this process in the discrete time case, right? So this is the continuous time case. So this output y of t is just the integral of the input signal from 0 until t, right? And then if I apply the Laplace transform to get the transfer function of this system, right? This is the transfer function of this system, right? So that is 1 over s. So I want to approximate it in terms of my, for a digital time axis, right? Or discrete time axis. So what do? We assume that we have already done our integrator, our digital integrator has already done the work until the n minus 1th point, right? That means I know y of n minus 1. So knowing a y of n minus 1, I need to find y of n. So how we can find y of n knowing y of n minus 1? By knowing the input signal value at sample number n minus 1 and sample number n. I can just approximate the height of the signal for these two, in between these two sample values, and multiply it with the time value. So was okay? Exactly. So I'm just approximating this thing with sort of a rectangle. Clear? Okay, and that is what x of n plus x of n minus 1 is the divided by 2 is the average height of the signal during these two samples, right? Times t. Clear? Yeah. So rest is simpler. So what I'm gonna do, I can just apply the z transform of both sides, because from here I'll just find the transfer function representing this digital integrator. So I have a transfer function then representing the digital integrator. I have the transfer function representing the analog integrator. I'll then equate the two because those are related. One is the approximation of the other one. So that will give me the relationship between the z domain and the s domain. Clear? Clear? Clear. All right, let's do that. So let's take the z transform on both sides. This is y of z equals z to the power minus 1 y of z plus I have maybe, yeah, x of z plus z to the power minus 1 x of z, and this whole thing multiplied by t over 2. Clear? And then I can, move things around and take common. For example, I can move z to the power minus 1 y of z on the other side. I will get y of z 1 minus z to the power minus 1, and in this side I'll take x of z common. I will have 1 plus z to the power minus 1 times t over 2. Clear? Okay. And then I, move things around. I will have y of z over x of z, which is essentially the transfer function h of z. I can get it by moving x of z to this side and 1 minus z to the power minus 1 to the other side. So I will have 1 plus z to the power minus 1 over 1 minus z to the power minus 1 and times t over 2. So this is the transfer function representing my discrete time integration. Clear? So far so good? Questions? All right. Now I have the transfer function representing the analog integrator, which is this one. I have the transfer function representing my discrete time integrator, which is this one. What I'll do, I'll just equate the two together to get the link between the z domain and the s domain. Let me say this is equation A, and let me see this is, let's say, equation B, yeah, and then equating A and B together, yeah. So I will get 1 over s equals t over 2 1 plus z to the power minus 1 over 1 minus z to the power minus 1, and then from here, yeah, let me see, hopefully it's not gonna do it now. Yeah, it's strange, because last time it was not it was fine once I did this thing. Anyways, all right, we'll see. So then, I just simplify this. I just invert both sides. I'll guess s equals 2 over t 1 minus z to the power minus 1 over 1 plus z to the power minus 1. Apologies for the flickering of the screen, right? It's beyond my control. All right, so yeah, and then this is the bilinear transformation. And then from here, I can also move things around. This can also be written as z equals 1 plus st over 2 over 1 minus st over 2. Clear? So this is essentially a relationship between the z domain and the s domain. And then we can use this relationship Once we know the transfer function in the S domain of a certain specifications, we can convert that into transfer function in Z domain. Does that make sense so far? Any questions so far? Yeah. Now you can also verify. Wait. Yeah, not here. Windows E. Okay. You can also verify. You remember, if you have the left half plane on the S plane, that was mapping to the interior of the unit circle, right? The vertical axis mapping to the j omega, vertical axis mapping to the unit circle, and the right half plane mapping to the exterior of the unit circle, right? So you can also verify that the same thing is true in this case as well, right? So in this case, you can verify that this left half plane will map to the interior of the unit circle, the right half plane map to the exterior of the unit circle, and the j omega axis will map to the unit circle. So, all right, so let's do an example in which we will have the transfer function for an analog filter, and we will convert the transfer function into a digital filter. Let's do that. Given an analog filter whose transfer function is h of s equals 10 over s plus 10, convert it into a digital filter and find the difference equation. And sampling interval is t equals 0.01 seconds. So you have an analog filter whose transfer function is given by h of s equals 10 over s plus 10. You can need to convert it into a digital filter and find its difference equation when sampling interval is 0.01 seconds. Clear? All good? Yeah, good. Okay. All what we will do, we'll just apply this bilinear transformation. This bilinear transformation will just replace s with 2 over t 1 minus z to the power minus 1 plus over 1 over 1 plus 1 plus z to the power minus 1. And the sampling interval is 0.01 seconds. So t is 0.01 seconds. This implies 1 over t is going to be 100. So transformation will become s equals 2 over t, which is 2 times, so 2 over t, you have 1 minus 0 to the power minus 1 over 1 plus 0 to the power minus 1, which by the way you can also write it as 2 over t z minus 1 over z plus 1. So here, since 1 over t is 100, it's going to be 200 times z to the power z minus 1 over z plus 1. So I'll just replace s with this thing. So when I do that, and the equation in my example, so I had h of s equals 10 over s plus 10. So h of s being replaced with 200 z minus 1 over z plus 1 means equals 10 over 200 z minus 1 over z plus 1 plus 10. I can take things common, or I can, let's say, divide by 200 on both numerator and denominator. So let's do that. Let me pull up my calculator. So calculator, okay. So 10, I can just write this as 10 over 200 over z minus 1 over z plus 1 plus 10 over 200. It's going to be 0.05, 0.05 over z minus 1 over z plus 1 plus 0.05. Okay, and then I can, it's just algebraic manipulation. Then I can take the LCM and move things around. It's going to be 0.05 times z plus 1 over z minus 1 plus 0.05 z plus 1. And this guy is just 0.05 z plus 0.05 over so z minus 1 plus 0.05 z plus 0.05. This is just 0.05 z plus 0.05 over 1.05 z minus 0.95. Yeah, and remember, make your transfer function in the standard form, right? So in the standard form, this is 1. So what I'll do, I'll just divide both numerator and denominator with 1.05. So I will have 0.05 z plus 0.05, this whole thing divided by 1.05 over, I have 1.05 z minus 0.95, this whole thing divided by 1.05. So let's say 1.05 c, right? So when we do that, I have 0.05 divided by 1.05 comes out to be 0.0476 plus 0.0476 z to the power minus 1 over 1 plus, then I have 0.95. So 19 divided by 21 is just 0.90476 plus 0.90476 c to the power minus 1. So this is a transfer function. Clear? And then from here, I can find the difference equation representation, right? And how can I find the difference equation representation? Yeah, so I can just make it in terms of y of z over x of z. So this is y of z over x of z equals 0.0476 plus 0.0476 z to the power minus 1 over I have uh, 1 plus 0.90476 z to the power minus 1, and I can you do cross multiplication, move things around, take the inverse. I will have y of n equals 0.0476 x of n plus 0.0476 x of n minus 1 plus 0.90476 y of n minus 1. So this is the corresponding, not plus, minus. This is the corresponding difference equation representation. Just to summarize, right? I have the analog filter, which was h of s equals 10 over s plus 10, right? All what I did, I just converted into discrete time digital filter. How? By just doing the bilinear transformation, which is 2 over t, 1 minus z to the power minus 1 over 1 plus z to the power minus 1 over 2, or 2 over t, z, to power, z minus 1 over z plus 1. This t is 0.01 seconds. So that became, 1 over t became 100. So 2 times 100 is 200. So then I just replaced s with 200 times z minus 1 or z plus 1. And just did that, do the, algebraic manipulations, and then this is the result that I get. Clear? Any questions till this point? So now you know that given the the transfer function of the analog filter, how can you convert it into the transfer function of digital filter? All what you need to do is just apply the bilinear transformation. Questions to this point? All good? Yeah? Sorry? We don't need to, because we just need to design the digital filter. Right? So, yeah. Yeah, but you can do the opposite as well. So let's just stop recording for this one.